So we're going to talk about two terms that are used interchangeably. And Nick's taking this class with Don Smith where you guys are addressing these concepts. So hopefully he can educate us a little bit. I never took a course on distributed computing, so I'm inventing things here. But just from a knowledge of English or what you might have seen in your assignments, how might you define consistency, consensus, and how might you separate them? If you can separate them, or they're interchangeable. Yeah.
Well, I guess consensus would be that, every client agrees on, maybe even like a state of consistency is that they all, are true to what that state should be.
Okay, so you're saying in computer science we talk of clients. In real world we talk of parties, there may be human beings and so forth. So there's something on which they all agree. That's consensus. And consistency? Let me try to get answers from other people first, then I'll go to Nick for rescue.
I think would something be consistent if the same action produced the same results with it?
Okay, so something could be consistent. So is consistency involving one you're saying, so the same action across, okay. So there are multiple agents, and the same question asked to each one of them yields the same answer? Okay, same question gives the same answer? Yeah.
I was going to say that.
Okay. So how are they related? Are they totally independent concepts then? Does one result in other? Does one need the other? Is one using the other mechanism?
I would think that a consensus could lead to consistency, but you could have consistency without consensus.
Okay, so you're saying consensus could lead to consistency? If they all agree? Okay, Matt?
It seems to me like if you have consensus, then consistency is easier, and also the other way around. If you have consistency, then consensus is a little easier.
So you're saying they have some kind of symbiotic relationship, that one helps the other, and so how could consensus? How could consensus help consistency now?
I guess if they all agree to perform an operation in the same way, then I guess it could lead to all of them
Having
going to the same place.
having the same state?
Yeah.
Okay, Matt?
If they all agree on the state of something, then whatever method or whatever that they call based on that state will be consistent across the different clients.
Okay, so if we all agree that, the exam is postponed to this particular date, then we are consistent also. Right? And how could, so we've said that consensus leads to consistency. How does consistency lead to consensus? So if we all agree, we use the word if. What if we don't agree?
So I'm starting to ask myself, do these clients necessarily have to know that there's a bigger structure, that there's other clients?
Okay, so does each party, let's be very general here. Does a party have to know there are other parties? Yeah, if you're working alone, then the world's right. Maybe the client as an application program is oblivious to this. Maybe there's some underlying functionality that the system library provides, the language provides, that achieves this, but somewhere there has to be awareness of other people. So we said that, look, if we all agree that some state is to be reached, then maybe we'll also make that our state. So we'll become consistent. But how can consistency lead to consensus? Consensus can lead to consistency. Consistency can lead to consensus. Nick?
I don't know if I'm misunderstanding here, but it seems to be a trivial point that consistency, if you have consistent representation of data across multiple parties, and if you ask those parties, if they have the same thing, obviously they're going to say yes. If they have
Okay, so that's good. So consistency can lead to consensus. If they're all consistent, then they can all agree on the same value. So that's kind of trivial. So the other part where consensus leads to consistency, the question is, do they all agree to have the same state? Maybe they're autonomous. If you're going to postpone, if you're going to add an extra credit assignment, maybe we have to first agree, and then agree on the agreement, agree on what we agreed on, and make that consistent. Okay, so these terms are used quite interchangeably. Just from the English thing, let's say we change some requirement in the course, like we added an extra assignment. So I propose a change. I say, actually, in this case, Brennan proposed a change. He said, hey, how about having an extra credit assignment? Okay, so he told me, and I said, okay, let's talk to the class. So there was, everybody in class. Matt wasn't there that day. He was helping us propel to victory. So everybody said yeah, so we voted, but then we had to go and let the result of the vote percolate to everybody, including Matt, who was not in class, right? So we need to go and make sure that everybody has the same answer. If they ask, is there an extra credit assignment or not, everybody's giving the same answer. So we then had a consistency. So and then we have consensus. We had an algorithm to make things consistent, and then we had consensus that everybody knows the new changes about the new change. Okay, so this can happen in processes. This can happen in real life. Okay, so they're kind of if there's no vetoing, if it's just a question of propagating state, then consistency helps consensus. Okay, but if there's a question of vetoing, then consensus is necessary for consistency. Okay, that we all decide, okay, the majority voted, so that is now going to be our state. Okay, so you can see now how this problem is a bit involved. Okay, a bit is an understatement here. Okay, so consensus. So when somebody proposes, we first try to agree on whether the proposal should be accepted or not. Okay, so we run an algorithm that's a consensus algorithm, right? And there's many ways to reach consensus. We could require everybody to agree, okay, which is what I wanted, or we could say the majority. Okay. So once something has been agreed on, we run a consistency algorithm to make sure that everybody gives the same answer to the question, same question, right? But that will take time. It won't happen instantaneously because this is a distributed system. So then we need consensus on or awareness of who knows what, and we say, okay, now at this point everybody knows, and we can schedule the assignment. We can change our things. Okay. So how hard do you think is this consensus problem? I said a bit difficult. Matt, you have a question?
I was wondering, so the consistency algorithm cannot run until the consensus has been guaranteed.
The first consistency algorithm, there's two consistency algorithms, right? One is, do we agree? And then consistency is on the agreement itself. Right? So they're going one after the other. So first I have to go and let you know my proposal. Then I have to let you know the verdict. So how many such rounds do you think will be required? Or let's just say, how hard is this problem, you think? Nick's seen a lot of solutions in the class probably.
hard.
It's pretty hard.
I know it's very hard. 'Cause
Is it hard like in, oh, you've got to prepare 1 week for your, when is your presentation, today or tomorrow? Tomorrow. So is it hard like you have to read a lot of papers to present, or is it hard like an impossible?
I don't think you could guarantee a solution.
You don't think you can guarantee a solution? So why do you think so?
Because it seems like you could have some sort of cycles where if you have two clients that disagree, one could switch to the other ones, and then, so if one thinks we should do option A, and then the other one thinks we should do option B, there could be a situation where they keep flipping opinions. And
Okay.
never reach consensus.
Okay, so one question is, do we even reach agreement? Okay, if there's only two people involved, and one proposes one, the other proposes the other, and there's no majority. Or if the algorithm is not smart, like you're kind of implying, each one accepts what the other person is doing, so I accept your proposal, then I let you know that what the new proposal is, you accept that, and we can get into some kind of cycle there. Nick, you want to say
I
something?
think it's doable in majority cases.
So if you have majority, you think it's doable.
I mean, like, on a very extreme case, you can break the consensus, but you come up with algorithms that basically guarantee can be, well, like, it can always break in the middle of nowhere, especially with network involved. But, our current algorithms have improved and, reduce the possibility of that happening.
Okay, so you're saying current algorithms reduce the...
It may not succeed in the first try, but it will keep doing that.
Okay, so given enough tries, you think it can achieve consistency, especially if you have an odd number of, if we agree on majority.
Yeah.
And the question is, the problem is doable or not doable means that can we reach consensus on whether we have an agreement or not? It's possible we don't have an agreement. As long as we achieve consensus on that, we've solved the problem. So even majority is not necessary. It's just that we should all agree on what we agree. Okay? You said something about network problems. So what
So
network?
that was more about, sort of related to my presentation.
Okay.
Because my presentation was how broadly distributed data storage is, how the replication and, making change each of the replica would sync up with the rest of the replicas, and how the current read operation would interact with all of that.
Okay, so you're saying your talk involved some networking issues and how the read operations and write operations interact with each other. Right. Okay, so let's we are all nerds and we're going to processes and clients. So let's go. Before we go to that, what we're going to do in this, so this subject is studied a lot. Okay, often people think of distributed computing and consistency as synonymous. Okay, especially if you're looking at theoretical algorithms. Okay, so what I'm going to do is I'm going to only skim the surface here, and part of the reason why I've delayed this lecture and why I wasn't even fully prepared before I came here is because there's just so many options here. This is a very deep subject, and I was trying to just figure out what to present, how to present, what your assignment should be, and But being a systems person, and this being an undergrad class, we will look at practical algorithms, quote unquote practical, of course. You can try to prove them correct, but we will do some of that, but it will rely on intuition a lot. And like I said, I had to first make a choice as to what to present, then I had to figure out how to present them. And the way I like to do it is to sort of have the algorithm be derived in class, okay? And these are complex algorithms, as Nick has been telling you. So deriving them in class is going to be challenging, so the way to do it is to come up with some intermediate algorithms in between and form a path from the really simple algorithm to the most complicated algorithm, okay? So there will be some incremental algorithms that will be my algorithms, no proof there, who knows whether they work or not, okay? And many of these algorithms I've learned recently, so even what I present may not be correct. So please look at this very carefully, okay? And also, I want to look at it from a systems point of view. So I seem to be saying that I'll do a little superficial job, intuition and so forth, but I want to do a more thorough job in abstractions, okay? So these algorithms that have been presented have been application independent, okay? If they're indeed application independent, I should be able to come up with an abstraction that is application independent also. And especially if I want to give you an assignment, I don't want you to implement all the grungy details. I want you to take something that is simple, does all the grungy, simple algorithmically, but takes care of all the details that are required in almost any consensus algorithm, and build on that. So we'll be trying to formalize an abstraction, and I'll in fact, and so another reason why I've taken time is I've been trying to implement it while I've been trying to prepare the lecture. Okay, so that will give us some depth, but overall it's going to be focusing more on breadth than depth. Okay, so talking of intuition, let's take a classical problem here. Okay, so two armies of the same, two collaborating armies want to attack. They're in two different valleys, and they want to attack another army that's in a third valley. Okay, and the consensus is that what is the time at which we attack. Okay, so let's say the initial state is that they both think it's dusk, or the initial state could be that they both don't know what the time is. Okay, and there's one leading general. Okay, so one's going to decide. I'm just making the problem simple. Okay, and the leading general decides that it's going to be done at dawn. Okay, the leading general is looking at the army to be attacked and says, oh, they don't wake up early, they're late risers, so we'll attack at dawn. Okay, so the way to go about doing this is to send a messenger to the other army, right? Now the only path to the other army is through the valley, and the messenger can be captured or worse. So what's the algorithm we should have here now? Okay, so we send the messenger, and the messenger, let's say, makes it. Okay? Now what should happen?
They need to acknowledge the guy.
You need to tell the other guy that, hey, messenger made it. Right? So you say, fine, it's at dawn. You know it's dawn, but they don't know. General 1 doesn't know what the General 2 knows. Okay? So we send another messenger. Are we done?
You could go intensively because then the one on the right side wouldn't know the one on the right side.
So now we're going to tell the other party that, hey, I got your messenger, because he could have been,
Yeah, you could have gone like practical.
right? So we send an ACK of an ACK. I told you, consistency, consensus. How many rounds are we going to have? Okay. So we need an infinite number of ACKs. Okay. So how do we solve this problem? Yeah.
You send back the original messenger?
Okay, but we still don't know whether we send back the original messenger or not. The other party doesn't know whether that messenger made it or not. So the other party doesn't know what you know. There's no cell phones here. We are talking of just communicating via messengers. So what do we do? Seems like an impossible problem to me.
So for the non-leading general part, you would basically have to assume that your messenger goes back fine. And, like when you get the prepared, you send back. So you send a message say I'm prepared, and sends it back as and the say okay you're prepared.
You're saying that we'll just have to live in an imperfect world, and not assume absolute consensus. Yeah.
This is kind of like that. So you send over general, or messenger 1 goes over to the second one, tells them a thing, and then goes back, or attempts to go back. The second hill with general 2 has to assume that what is said is correct, unless it sends over another messenger, and the first group will send over another messenger if it doesn't receive the original messenger back in time.
In time.
Like have a timeout. Say,
So, by the way, this messenger getting captured is in computer science, in computer networking equivalent to? Sorry?
sending over a segment.
And when you send a message on the network, it can get delivered or it can get lost, right? So how do we get reliable communication? We talk of TCP/IP having reliable communication, yet I've just proved to you that we can't have reliable communication. This is so. How hard is the consensus problem? It's actually impossible. We have to rely on quote unquote hacks ultimately. And you kind of hinted, Brennan kind of hinted at what the hack might be, but what is the hack that TCP/IP uses to guarantee reliable communication?
Segment numbers.
Sorry?
Segment numbers.
Segment numbers, and that's for duplicate messages. And you send duplicate message because you timed out. Okay? So what do you end up doing? I hope my animations here are doing that. Okay, I'm just trying to show here that this is info. So can never achieve consensus. Okay, that's a theoretical result. It's like the halting problem. Okay, you can't do it, but halting problem doesn't halt us from trying to solve it, right? We keep coming up with approximate algorithms. So we'll try to come up with approximate algorithms. So you send messenger, and I guess I shouldn't have had that one slide. If you didn't get an ACK back, you send the messenger all over again. Send duplicate again, right? So what we can do is, don't look at this right now. Just tell me with timeouts, how can we solve the problem of consensus? How do we exactly know? How does the sending general and the receiving general exactly know when consensus is reached? Assuming we have timeouts. And I've got an algorithm here, but I meant to show this with animation. I didn't. So just try to think without looking at this. Yeah.
A consensus is reached when the first general gets back that after from the second general.
So consensus is reached. If the general gets an ACK back, we know consensus has been reached. And how does the general know that consensus has not been reached?
If the timeout is reached before the actor comes back.
Okay, so, and you might send more than one ACK, right?
Mm-hmm.
So then can we refine that? So there is some timeout for sending an ACK, and there's some number of ACKs you send. Depending on these two, you keep sending ACKs, and if the last ACK is not ACKed within time, and you had to send the last ACK, then you know consensus is not reached, right? And the receiving general, when do they know that the consensus is reached?
When another dude hasn't come over, so when another messenger hasn't.
When they haven't received a duplicate message for a while. Okay, that's what I'm kind of seeing here. I hope I've got it right. Okay, so if generally, if the number of retransmissions you've done is less than the limit of number of transmissions you'll do, I'm not, you guys have probably, this TCP/IP algorithm better than I do. Is the timeout between ACKs the same, or does it keep growing? So if I don't receive an ACK within time T1, I send a duplicate message, right? Now, do I again wait for time T1, or do I grow the time T1? Or is that?
You grow it, and as soon as you get a successful one, you reset it.
Okay, right. It's been a while since I looked at, yes. So I'm assuming here that T1 is kind of constant, okay? And so consensus achieved if ACK received after less than R transmissions, okay? And otherwise it's not. And consensus achieved in the obeying general algorithm if no retransmission received within some time function f, that's a function of the timeout and the number of retransmissions. Assuming timeout is constant. Okay, I'm simplifying things. Okay, so the point here is that consensus cannot be reached instantaneously. It will take some time. Okay, and it cannot be proved completely done, and we need some hack. We need to have some heuristics. Heuristics is a more erudite term for the term hack, and we use heuristics to go and reach consensus. Okay, questions so far? I'll try to clean up. So here's how we will model the problem, okay, in computer science. That we've got two processes, okay, they're coupled. It's like the generals. They're independent agents. It's not that they're replica of each other, but they're sharing something, okay, and they may be sharing more than one thing. Okay, so there may be object O1 that you're sharing and object O2 that you're sharing, and you want to make a change to this object, and you want to agree on these object change values. Okay, so we might have multiple objects. So now I want to convert this into an abstraction now. Okay, so let's see where I'm going here. Okay, before I go there, what are some practical examples of consistency, in computer science? Okay, we've taken the general problem, we took the voting problem in our class, but before I try to come up with the abstraction, what are some examples you can imagine or you know about in distributed systems that you know about or can imagine?
The Bitcoin network, I don't completely agree on the ledger transactions.
So when you do a transaction in any kind of network that allows money to be exchanged, you better agree on it. Agree, right? So if I go to Schwab and I say I want $1,000 from my credit union, we better agree. Both the credit union and the Schwab better agree on this transaction, right? So that's good. How would you classify this kind of interaction? Okay, so Bitcoin is one example you gave. I give credit union. How might you classify this? Oh, I'll come to that. I'll come up with some pictures and we'll try to classify that. Any other examples? So I want not only specific examples, I want categories.
If you open your email client on different clients, you should get the same mailbox.
Okay, so you've got your mail somewhere, and that server is talking to multiple email clients, and they should all have an agreement on what your emails are. Okay, Brennan?
If multiple people have opened the same Google Doc, you should see changes in one reflected across everything.
Okay, so if we are editing Google Docs, we should all have consistent change inserts and deletes and replacements. Other examples?
Our computer science passwords, I don't know how that would be, but we can log it, or like onions and so like credentials for different sites. I don't know how it's set up. If it's one main, I know onions one main login, but I don't know about computer science because there's a lot of different a lot of different machines that we SSH into.
Okay, so you can SSH into multiple machines
With the
and
same credentials, yeah.
with the same credentials. So the credentials should be consistent across all the machines.
Yes.
And there is this whole, you guys are living in this new world, but at one time single sign-on was such a big deal that everybody was proposing single sign-on. And now you can take your Facebook credentials and go to Microsoft, and you go to a lot of places, and you can just take it for granted. But there was a long path to this okay, kind of consistency. Other examples? Nick?
One was because I'm still sort of hang on my presentations, that you could have replicas in North America and Europe, and no matter where you retrieve that piece of data, it should be the same.
Okay, so just like Matt said that, if there's one Google account and from all laptops I should be able to access the same state. What you're saying is, and there was client server, Now you're saying in North America you might have one server, in South America you might have one server, and they should, and each server will maybe serve its local clients, and the server should be consistent. Okay? So I think we've pretty much touched on, anything else? Yeah, Jake.
Like routing tables?
So routing tables, another data structure, just like credentials, they should be consistent. DNS name entry should be consistent. Okay, so now you have multiple agents making changes perhaps, and they should all be consistent, right? So it's an important problem. Okay, so and let's try to classify this. We've got a lot of points here, and I've got some categories here. Let me know if I missed a category. Okay, we'll try to fit your examples into the categories I show you. Okay, so you're taking a quiz. Any consistency issues here? Have you guys ever seen a lack of consistency here? Yeah, so firstly, when I go and put the quiz, you should also see the same quiz. What about submitting a quiz?
Are you talking about like some of us do the quiz early and then after we submit it, you change the...
So that can, okay, so there's concurrency issues, okay? That after you submitted, I change it, and that's a problem. But the first time I gave a quiz, a student came to me and said, I committed, and it didn't take my commit, or I never got notification it's been committed, and that was, that's a very big deal. What do I do? What do I do with the student now? Do I open it for everybody? Do I open it for that student? So things can go wrong when you submit it, okay? And especially if let's look at your class participation thing, okay? You go and edit it, you submit it, and it says sorry, data's passed, and in the meantime you submitted it and you just shut your laptop and maybe even shut it down. So your answer's all gone. So you need to know that the server knows what you know. Okay, so you need the server and you to be consistent there. And if it's not consistent, you want to go and save your data for the quiz next month, right? So this is an example of a client. What's really happening? So what's a general problem here? I could be submitting my tax returns. I could be doing a lot of there's a lot of things that can happen. A lot of examples of this. So the general problem here is you've got a server, you've got a client. Yeah, so basically it's a client server, and the client's providing you the user interface. Okay, the user interface is duplicating some of the state in the user interface has to be mirrored it has to be saved onto the server. Okay, so we want that to be consistent. Okay, here's something else that is kind of different, and it touches on something that Hunter said. So Travelocity, I want to make a flight and a hotel booking. So how is this problem a little different from the previous problem? So I'm going to San Francisco. I'm going by United, coming back by Delta. Okay, and I'm also booking a hotel.
You have to deal with multiple servers.
You have to deal with multiple servers.
You also gotta, when you submit, you gotta confirm that flight is still available.
It's still available. Have you guys had the problem? Oh, this what I'm talking about is not, I didn't just pull it off from a hat. So I was booking my flight to San Francisco, and I got a rate, and when I went to commit, it said, sorry, the rate's gone up by $500. Fine, but I went and got back the data, it still showed the same rate, so I did it again. I'd been changing my credit card, and this time it went through, but charged me $200 extra. So you can see how consistency is as it turns out, they give you. So this is the interesting thing. This is Travelocity. They charged me $20 extra. Now, I didn't complain to them. I didn't complain to them because they give you 24 hours to cancel something. So there are sometimes social solutions to technical problems. Okay, I want to get into that at some point. That consistency is so hard that you sometimes don't even try to achieve it. Okay? And today, I don't know whether you guys have heard the news about the United Airlines problem of overbooking. What is that overbooking problem? It's again a consistency problem, right? Sure, they sometimes overbook out of, just to make sure that their seats are full. But sometimes they overbook because the databases are not consistent. Okay? And they just say, oh, we give you 800, points or $800 ticket and you'll be happy. And maybe some social solutions like that work most of the time at least. Okay? So what we are going to talk about here, and this is the same example as the transferring money from Schwab to credit union. Okay, I've got two servers involved. Okay, so what we've got here is a bunch of logical servers. Okay, and maybe the arrow that I'm showing maybe the arrow should be only from the left server to the right servers. And I'm calling this a nested transaction. Can you guys see why I'm calling it a nested transaction?
You have the transaction of booking the flight, the transaction of booking the hotel, and then you have the transaction of combining the two in an
Okay.
appropriate way.
So I have the transaction of the flight, and maybe there are two different airlines involved in the flight, and the hotel. So Travelocity, I'm submitting a nested transaction, a top-level transaction. It has to go and make sub-transactions in two other servers. And so that's a nested transaction. And again, when I go to Schwab, and I go and say I want to transfer money to credit union, there's the Schwab server involved and the credit union server involved, two servers involved. Okay, and so that's another application. Okay, and the arrows between the two right servers shouldn't exist, so I'll remove that. Okay, so another activity I've recently done is saved my changes to Git. So what's going on here now? Fundamentally different. So we had client server, one client and a server. We had multiple servers, with one server being the master server going to slave servers. What's going on here? In abstract terms. Jacob?
Multiple clients writing code or whatever.
So multiple clients writing, multiple clients. So is this the same situation as my taking the quiz in Sakai?
No.
Every client has a copy of the entire history or database.
Okay, so you've got now multiple processes. I don't know whether to call them clients or servers at this point. But indeed, this is a Git client. But you've got, in the previous picture, I talked of three logical servers. I said, look, there are three different entities. In the first picture, I talked of client and server, two different entities. Now we've got physical replication of some logical state. Why are we replicating it? Why am I not just simply interacting with the Git repository directly?
Because if a server dies, then you lose all the history. So if you replicate it across multiple clients or servers, then you have redundancy.
Okay, so you're answering the general question of why you might want multiple copies of data, and one of them is redundancy. But in the case of Git server is not going to die, right? Oh, is it going to die? But is that the reason why you really put it on your local computer?
You can work with it offline. You can commit and do things without being connected to the server.
Without being connected to the server, and even if you were connected to the server, would it be still advantageous to work offline? Because?
So that your mistake won't mess up entirely.
Okay, so there is question of whether your changes are consistent with some other changes or not. And you don't want to, maybe you want some delay before you share, yeah.
With version control in general, is it kind of more egalitarian? Because, each client could have the correct version and a newer version is better. So consensus really depends on what the goal is, I guess, of the program.
So what Nick is pointing out is a problem actually rather than a solution. So he's saying that, look, Consistency may be hard to achieve now because you've diverged and you're checking in, right? And then you're saying that, look, there can be multiple, each one, maybe consistency is good, or we have to figure out what the consistency is, right? What the right solution is. But I'm trying to get to a much simpler thing, that the reason I might want to work on my computer copy is, A, I want to diverge a little bit, before I don't want the world to see my half-baked ideas. Okay, and this happens to me, by the way, all the time, that I'm doing this, I'm adding all this code here, and some of it's not even compiling, and I have to make sure that every time I deposit something into the Git repository that you guys are taking things out of, it's at least compiles. Okay, so that's part of the reason why I get late sometimes coming in, because I better not leave it in an inconsistent state. So I want to diverge, and that's sometimes good, but diverging creates problems. But even modular, assuming there's no divergence, I might still want to go and work on my local computer copy, A, because I'm offline, B, because I
I'm sort of going back to why there is a version control, why we need a version control, is that you want.
Let's forget version control for a moment. Let's assume divergence is not an issue. Okay? And so, yeah.
So you could want, say you're working on one specific module, and then some other person is working on another specific module. You don't want their changes to mess up your working copy, so that you can both improve it independently and then.
Okay, so you're saying again that we want divergence so that we can have the half-baked ideas not shared, right? But again, I'm looking for a very simple answer. Let's forget version control. Let's forget multiple versions. Okay, I want to work on my local computer because I'm offline. There's offline, online, and what's intermediate between offline and online? Sorry? Slow? Okay, I thought I heard that. Okay, so I might be doing it for performance. That's like my server in South America. Okay, so the replication is achieved both for fault tolerance and performance and versioning, as we've seen here. Okay, so we've got physical replicas now that have to be kept consistent. Okay, and in the case of Git, what we are sharing is, what do we really send to the other parties when we want to share our changes? Changes in the history. So just the changes, not the complete state. So we're sending diffs. If we want physical replicas to be consistent, what else could we be sending them? Google Docs, when you're doing a binary image, it probably sends the whole thing. I know, because when I'm saving my PowerPoint with audio and it's 40 megs, sometimes it's quicker for me to drive over from home here than for the 40 megs to reach here. So depending on the connectivity. So and then what else could you be sending? You could be sending the whole snapshot. You could be sending diffs. What else could you be sending? Have you guys been creating physical replicas in your project? No? What are all your simulations? They are all the same state. In fact, why I gave you the simulation project was to give you the replication example. They're really physical replicas, and that's another reason for having replicas, to have collaboration, to sharing, so that multiple people can share something while running the application locally. And what are you exchanging there? Are you exchanging snapshot? Messages, but what are the messages containing?
Actions. Like the actions.
Each action. Okay? So you could send each incremental action. You could change the state and compute the diffs and send the diffs, or you could send the whole state. Okay? So we are doing this for reliability partly. Okay? I do want my changes to be saved on Git so that I don't lose them. Okay? I'm doing it for sharing so that I can share with you in a controlled way. And I'm doing it And I could, of course, we could all go and change the repository in the server directly, but I want performance. Okay, I don't want to be accessing having network delays. Okay, and in this case, the state shared is diffs. Okay. Here's my Google Docs, or Google Drive rather, not Google Docs. Google Drive or Dropbox, OneNote, whatever you want to take. And here I just hinted that at least because these guys deal with images also, they deal with all kinds of files. And people try to do little diffs or binary files too, but if you're supporting binary files, you're probably sending a snapshot. Okay? So I'm just trying to, just trying to compare them and say there are some differences. And then, when you're doing Google Docs, where as I change something, you see the change, which is equivalent to your simulations being consistent. Okay? We are actually sharing the next command. Okay? And when you try to go and I'll talk about this a little later too, but when you have multiple replicas that are being kept consistent with commands, the technical term people use are state machines, replicated state machines, that you're just sending the transition, next state transition to each, the transitioning command to each state machine. Okay? So we've got your Google Doc example here too, but they're all physical replicas. Okay, in your project, we are sharing the commands. What else are you sharing? We didn't want the commands sharing to involve consensus. Right? The consensus was involved in sharing what? Configuration. And what was the configuration? Exact configuration? What? Sorry?
Whether it's atomic or not.
Whether it's atomic or not? That's interesting. Atomic has to do with consistency, right? So we are sharing not only the state that has to be made consistent, but we're also sharing the state about consistency, the meta state, the configuration state if you want to talk about it. Right? And so one of the things is whether how strong the consistency is. Is it atomic or not atomic? We could be sharing communication protocol. That's another thing. How are we going to achieve consistency? Again, I'll talk the meta. Can you think of anything else that you would want to share that a lot of people talk about, at least you might have heard? Some meta state that you keep to control consistency? To make sure that consistency occurs? So you guys have all said how wonderful it is that I can work offline and make changes to my Git repository. Have you guys ever worked with somebody else on a shared Git project? How enjoyable are the commits? So in industry, people try to work quickly. They want to commit before you commit, because the headache of resolving the changes goes on the later person. Right? So how can we avoid conflicts? How can we avoid you making a change that conflicts with mine?
Work on other parts of the project, I guess.
Work for other projects. And how do we ensure that we work on different parts?
Like distributed log.
Locks. Okay? We could have social protocols. That's what Git has. Git doesn't, I don't think Git has locks. But in general, you could have locks. Okay? You could have locks that are on your file system involving multiple processes, or you could have distributed locks involving processes on different machines. Okay? And do you guys know of any example of an application you might have used that uses locks, distributed locks? Sorry? Old version control, one of the version control systems? Okay. Okay, so SVN does that. Okay. Any other tool? Have you guys ever used screen sharing? So there's two ways of doing screen sharing. One person is active and the other people watch. Right? or both people are active. Have you ever done screen sharing with both users are active? You haven't. You have?
Yeah.
Which tool did you use?
I don't know if Hangout still has it, but they did for a while.
Hangouts had it for a while?
Fix something on the computer, so.
So how did you manage? How did you manage manage who's who's interacting at one time?
Well, we didn't both do it at the same time. So I like socially locked my mother out and said, "Don't touch anything. Let me do everything." Even though she could have messed with me, I just said, "Stop."
Yeah. So you had an audio-video communication.
Right.
Anybody? So as it turns out, this is very tricky. In Google Docs, you can edit simultaneously. Shared tools, you can't. There's one stream of communication. Okay. As far as the application is concerned, there's one user interacting. So if I start dragging, and you release the mouse click, your release will finish my dragging. Okay. And you can end up the application can end up getting event sequences that cannot occur with a single user interacting, and the application can crash. So if you really want to allow multiple people to interact here, you need blocking, or you need social protocol. It'll crash. Okay, so that's an example of okay. So just give me 2 more minutes. So can you imagine there being one directional arrows here? In all these examples, there were 2 directional arrows. Can you imagine one directional arrow? Yeah.
So like when he said with helping somebody out with IT, you might assume that the person helping is the person that should be interacting, so it'll override.
Okay. So if the helping person is going to be the one interacting, or the helped person is going to be the one interacting?
Helping person.
Okay. Okay. The helping person could be interacting, but going back to what Nick said, you've got one server that's sort of making the changes, and then you have mirrors in North America and other places. So everything is going one direction. I mean, from the writable server. Okay. And here's a picture I just got by Googling. I like to give credit to people when I use other people's images, but I just couldn't find an author of this image. So I'm just, so this is just something from Google Docs. But this is Akamai is a company. Is it still going strong, the company?
We had a question about it on our 431 test, so maybe.
Okay. So the idea is that you've got an origin server on the right that they're talking about. That's where all the changes are being made. And then you have mirrors on the edge of the network, as they put it. And these guys are keeping consistent. So it's one person being changed and the others mirroring it. Okay? So we'll see there are many algorithms for consistency, and they're tuned for different classes of applications. And I'm trying to show you what the classes of applications could be. Okay? Okay, so what we were doing was looking at various real-world problems that motivate some kind of consistency and consensus. Okay, so we saw what that might mean. We saw that the problem is actually impossible without making assumptions about message delivery times, and then when we're going to make these assumptions, we want to be consistent with the actual scenarios in which these consistency algorithms might be useful. And we looked at some examples and then tried to generalize from the examples the general structure. Okay, so we looked at the problem of submitting a quiz to Sakai. So you've got some state in the browser that has to go to Sakai, and that's really an example of a problem in which you have a server that provides some functionality, and the server doesn't directly provide a user interface. The user interface is on a separate process running on your computer, and not every keystroke goes to the server, so which means that some state is cached in your client, and you don't want it to go to the server because you want to delay the commit. Okay, so when you commit the state, you need some consistency. So that's one example. Okay, then we saw an example we took the example of Travelocity, and Travelocity is a front end for multiple servers, and so you have to have your browser be consistent with Travelocity server, but the Travelocity server has to be consistent with the other servers that it delegates its work to. Okay, so this whole notion of delegation I'm calling distributed transaction, because that's a piece of work that has to be done in multiple places. And there's a top level piece of work, and then there's some children pieces of work. Okay, so that's called nested transaction. Now, nested transaction, if I define it properly and rigorously, I'll take a lot of time, but that's the intuition. Okay, if a transaction is a bunch of actions that have to occur, and there's something called asset properties. Have you guys seen asset properties in any course? Databases? You saw it in nested databases? Okay. Okay. So so that's a nested transaction. Okay. So again, these transactions have to have common state. Okay. Travelocity has to know that Delta or United has made the reservation, Hilton or Sheraton has made the reservation, and so all parties have to agree on this. Okay. And the one application area that gets a lot of play in these algorithms is replication. Okay, so when we're talking of consensus, we can talk of replication of small pieces of data that are transient or persistent data and full replication. Okay, so when you're talking of physical replication, we're talking of some state being there for a long period, persistent state being there in multiple servers. Okay, and there's a question of why the data state is replicated, and another question of how it's replicated. Okay, so this slide tells you how it might be replicated, and with some examples. Okay, so in Git, the idea is that you want the various physical replicas to diverge for a while, so that you're happy with your state, and then you do a commit. Okay, and so you're sending diffs over when you do the commit, or you can take a whole snapshot of a file and just send the whole thing. Okay, or you, as each command is executed on one replica, you can send it to the other replicas. Okay, so you won't get any versioning then, but that's another way of doing the replication. Okay, and the term replicated state machines is used for command-based synchronization. Replicated state machines also mean atomicity. I'm being a little loose here. I'm saying if you do command-based replication, it's replicated state machine, whether it's atomic or not, because Google Docs and Live Meeting do not provide atomic broadcast. Okay, so that's the two examples I gave because it's something we use and they're interactive. Okay, and another application, and this is, meta is always interesting, that you have some state and then you create some meta state to maintain that state. Okay, and you have a problem of consistency, and you're going to make some state consistent, and to make that to run the consistency algorithm itself may create some additional state that has to be made consistent. Okay, so one of the big problems is let me just move my laptop a little bit to the right so that I see some of you guys craning to not being able to see properly. Okay. Better? Okay. So one of the big problems in consistency is that when you have multiple people making changes at the same time, that's a problem. Okay, that's a problem in two ways. Firstly, it's possible that the replicas may diverge. Okay, even if you don't make the replicas diverge, the second problem is that these two actions occurred independently. They may not add up. Yeah, the replicas may be the same, but logically what happened may not be the right thing. You may have to reject one action, you may have to sort of compose them in a way that didn't make sense. So one way to prevent this is to have locks. Okay, so now lock is a state that has to be maintained among multiple, the lock itself may be replicated. You don't want to go each time to a server to see whether you have a lock for a data item or not. That's a lot of latency. You may replicate the lock itself. So that itself is something that's a candidate for consistency. Okay, and then we saw that not all replicas may be modifiable. Okay, so physical mirroring is something we saw where one replica is modifiable and the others are mirrors of them. Okay, the question so far? So let's talk a little bit about the reasons for replication. And we saw last time one of the reasons is divergence. Okay, So it's not really replica, it's replica at commit times. Okay. Another reason we saw was, what are the other reasons we saw? Why do you replicate? Why not just keep it all at one place? You see one reason given, yeah.
I mean, if you have many servers and this is all across the world, you would need multiple servers in, several continents.
You will need them because, I mean, you could reach one server. You need them.
You don't want the latency time between client and server to be too long.
Okay, so one is performance. Okay, and that's what the Akamai mirroring is giving you. Okay, and another reason, Jacob?
I was going to say load balancing.
Load balancing.
So, like,
Okay.
if you have one, also tolerance in case one server goes down.
Okay, so there are three reasons really. Two reasons can be clubbed under performance. Okay, that you don't want latency, and you want load balancing also. One server, even if everybody is in Chapel Hill, okay, we have this one big, one server may not be able to handle it, and some of us run grading servers, and that's a issue. Okay, so there's bottleneck, there's performance, and there's fault tolerance. Okay, Brennan?
I was going to say reliability.
Fault tolerance. Okay, so let's look at fault tolerance in more depth now. Okay, we've got really so far two configurations we've seen in the examples I gave you. Okay, and they are asymmetric when you don't have arrows going between every pair of processes. Okay, so in the mirror case, all the mirrors talk to one writable server. Okay, so whenever the writable server gets a write, it goes and pushes it to all the mirrors. Okay. In the case of Google Docs or Google Drive, you have one server to which multiple clients talk. Okay, they are writable. The clients are writable, the server is writable, but the clients don't talk to each other. They talk via the server. Can you guys see why this asymmetry might be an issue from fault tolerance point of view? Jacob?
If the main server goes down, then nothing works.
If the server goes down, if the server that is connecting all the clients goes down, if the writable server goes down, which is what we call the main server, then the clients can't talk to each other. What happens if a mirror or a writable client goes down?
If a client goes down, then the other client doesn't know until the server tells them that it's gone down.
Yes. So the other client doesn't know, but can the client come up? Can you So when something goes down, you want to restart it and allow it to get back the state. Okay. So if the client goes down, actually in Google Docs you might get a little you get a little message saying who else is logged on. And if it goes down, you will get some notification through the server. Okay, but if the client goes down and then comes up back again, can it get back its state, the latest state?
Yeah, from
The server, right? The server is guaranteeing the latest state. Okay, so if this goes down, it can come back up with the latest state. Okay, if the mirror goes down, it can get there. Okay, so the question is, so failing writable client to read-only mirror can get it from writable server, can get the latest data from writable server. Okay, what happens if the servers go down? You're stuck. Okay, so what are solutions for this now? A peer-to-peer system. So that seems to be a solution, right? That make those arrows, create some more arrows, right? So how would that work exactly? So my server, I'm Macy's. I've got a server which is being mirrored everywhere, or I'm Google Docs or Google Drive, and I've got a server to which all the clients are talking. I've gone down. What exactly would that mean? I would do what now?
migrate the server to another client.
So migrate the server to a client. What does that exactly mean? But you're in the right track.
One of the clients essentially becomes the
Okay, so we can let a client become a server, which is kind of funny because clients are not really servers. But sure, what we are saying is that so we won't call it server then, client then. Because if it's on my desktop, you can't. I'm not going to host the Google Drive server. So what would I call that thing that becomes a new server? I can't call it a client. I'll have to call it a server, right? And how would that server be distinguished from the server that just failed?
It might be a good idea for it just to hold changes that either any of the clients make until the actual full server comes online. So it's almost like a change server or something like that, like it monitors changes you might make.
Okay, so you're saying it just holds the changes.
Right, and then when the server comes back online, it will push back to the rival server.
Okay.
Stop it.
So it just holds the changes like a mirror does. Except that the mirror doesn't push the changes. And now this server will push the changes to the server. That's one way. We are distributed computing people. We want a solution that involves multiple processes. What if I'm a database person and I don't know about distributed databases very much? But I know about persistent store and stable store. What else can happen? What else can we do to restore the server? Now, this may take time, but that's okay.
You mean like a transaction log?
Just a log of actions you keep on. What kind of storage is that called? What adjective do you use for the kind of storage on what you keep a transaction log? So it's not in memory. If it's not in memory, it's on disk. Disk is an example. Memory is an example of a transient storage. Disk is an example of persistent storage. Very good. Is there something even stronger than persistent storage? How persistent is it? Am I guaranteed that my disk will never fail? So what's this? You guys, when you studied databases, did you learn of another adjective that is stronger than persistent? That's hard to implement, as it turns out.
Are you talking about RAID?
RAID is an example of replication, and so we replicate the storage itself. And and we replicate it to get what quality? Redundancy, fault tolerance. You guys haven't heard this term, stable storage? No? Or stable storage in database is very important. Okay, and I'll put stable in quotes because nothing is completely stable. But stable means you'll never lose the data. Well, to reduce the chance of losing data, you might have replicated disks and so forth. Okay, so what if it fails? Service fail? Well, we'll have a log or a file, and so what happens? A client issues a transaction, or does it, and this goes and before telling the client that it's all okay, writes the transaction to the log file, and then goes and answers back. Okay? And now if it goes down, well, eventually, the idea is that somebody will discover that the server's gone down. Okay? They'll restart the server. The server will say, oh, where's my log file? Which might be on a RAID. And it'll go and read the data. And when it's all reset, it's ready to serve. Okay? So this is a distributed system, but we didn't use distribution to solve our failure problem. We used just a log file. Well, there was maybe, you can think of the disk itself as being replicated and somewhat distributed. It's not on the computer, but that's a solution. So what's wrong with just this solution? You guys gave me a more fancy solution where we get it from another process. This seems a simpler thing to do.
None of the clients can access the log file. So
None of these clients can access the log file, but they shouldn't, right? I mean, that's my data. But they can access the server.
I mean, with this system, if the server is down for a long stretch of time, then the clients are just kind of out of luck.
If the server is down for a long time, and if you're a Facebook server, the whole world knows about it.
Yeah.
Do you guys know that people have actually called 911 when the Facebook server has been down? Really? It's like electricity going away.
I heard that once the Google server went down for all like it's like minute, and then it was like a quarter of the world's internet traffic was halted.
Was halted? Yeah, so the Google server's down, this problem, and literally I heard this, that 911 was called by a lady who said, my Facebook server's not working. So, we want this time to be low. And the other issue is, why did the server fail? Something went wrong, right? If something went wrong, maybe what's in the log file is also wrong. Maybe when I read the log file again, I'll again crash. Okay. And what went wrong may have to do with the program itself, or it may have to do with machine idiosyncrasies. Okay, when we say replicated, I have to put it within quotes. We said, we'll execute the same command on all machines. We are assuming all machines will behave similarly. There's a lot of differences between machines, and you may not have ported things right, and something may have gone wrong in the machine. So you guys might know that in a spaceship there are multiple computers doing the same task. And they go in, and how do they decide if 3 computers say one thing and 2 computers say one thing, how do they decide what the right thing is? Maybe majority, hoping that the majority is correct. Okay? Or we can assume that, we can say, okay, we decide that the value is correct if all of us agree. So we can, what is that? Is that called plurality? When you need something, no, that's not plurality. What is it when you have to have complete consensus? That's called consensus, I suppose. Unanimity, sorry. Yes, thank you. Unanimity, of course. I used to watch a BBC show called Are You Being Served? Have anybody heard of it? No? So there's this lady there who's a real character, and she said, I'm always unanimous. I'm unanimous in this. So there was a contradiction in terms there, but I got reminded of that. Okay. Kevin hates that show, so he thinks that this is a cultural thing. It's a BBC show. So now we are getting to reasons why so log file error, okay, and we can create multiple disks RAID to create stable storage. But what if there is corruption of the master or the stable storage, and there's downtime? Okay, so this is not an ideal solution, though I think a lot of places employ it. So we'll do what you were talking about. Okay, what Hunter and Sam together were talking about. So again, I have a writable master. So now I'm going to distinguish between servers. Okay, so the term master slave is used here. The primary secondary is used here. So we have a writable master, and we have read-only slaves, okay, which are just like mirrors. And so they're like mirrors in the sense that reading client can get data from read-only slave or from the master, okay. But a writing client must go to the master, okay. And as we'll see, these slaves are not dispersed; they're in the same data center. So we are getting some fault tolerance, some load balancing, but not necessarily latency solution. Okay. And now this master goes down, and what should happen at this point? We want to solve 2 problems, right? We want to solve the downtime problem, and we want to solve the problem that the master itself might have got corrupted. So how do we solve the downtime problem? Which Sam kind of, Brennan?
Would the writing client itself become the master?
No, the clients can't become masters. Clients are on desktop. You can't trust, the company, Facebook can't trust me, right? And I don't have the load itself. Yeah, Jacob?
One of the read-only slaves becomes the new master.
Okay, so we need some protocol here. Okay, that's what I think your assignment is going to have, by the way. That you'll have some centralized process, and it'll go down and some other one. Okay, I haven't quite worked it out. Okay, so the writing client can't go there. What's going on here? Okay, sorry. So I'm trying to solve the two problems independently. Okay, let's just solve the corruption problem right now. So we have a downtime. Okay, that's the next slide. We'll do one. Right now, the master comes back up. Okay, and the writing clients are out of luck. Okay, but now the writable master gets data not only from log file, but also from the slaves. Okay, so it may get it from one slave, and get another slave, and may get it from log file. Okay, and now it can take a vote and say, okay, you know, if the two slaves are different from my log file, I'll use the two slaves data. If my log file and another slave are consistent, are together, and a third slave is out of sync, then I'll take that value. Okay, so we can have some algorithm to decide what the correct data are. Okay, and that can involve my log file and can involve the other slaves. Okay, so the point is that the arrows went in the other direction now. That so far the master was pushing data to the slaves, and now the slaves can push data to the master also. Okay, so this is the simpler algorithm. Okay, and what you guys had come up with was the more complicated one, and that's so far, yeah.
So if you, right before the server went down, if you had just updated the slaves and they had the same corrupted, data that the log file has.
Yeah. So
do you
it's
have any chance?
so why did so the question is, what if the slaves also have corrupted data? So why the master pushes the data to the slave writes to the file. Maybe the master's write got corrupted and the slave write did not get corrupted. Okay, so that could be a reason to go to the slave. Okay, and maybe the slave has not even looked at the file. The slave just looks at in-memory data and sends it back. So we don't even have to deal with that. Okay, the point is, why did the corruption happen? We don't have a good idea here, so it's difficult to answer the question without that. But and by the way, have you guys ever faced corruption problem in the computer? Yeah.
I've had it to a USB.
Sorry?
Some sectors in a USB were corrupted.
Some sectors were corrupted, so the disk got corrupted. Computer operating system. So, I worked on operating systems, and I never knew when something went wrong, whether it was the hardware that was going wrong, the kernel that was going wrong, the high-level layers that were going wrong, or the application program that was going wrong. And there was this one example where my partner and I were trying to get a assembly language program working, and this was in Madison, and it just wasn't behaving correctly. And we traced it down to the registers. We had that computer right in front of us, and we finally figured out that 2 and 2 was not 4 in the accumulator. I mean, that's what was happening. And we had to give a demo the next day or give the result of the demo next day, and it was a cold night in Madison. So we opened the windows saying maybe that'll cool the machine down and some bit will get unstuck. And it did. And we got the result. Okay, so war stories. So we don't know, but things like this can happen. And maybe it won't happen on other computers, so what you saved was correct. Okay. And the issue obviously was that the machine had got hot. Doing a little experiment. Just imagine how hot these machines can get when they're servers for so many clients. And one of the biggest problems at data centers is how to keep the cooling system efficient. Okay.
Error correcting code memory, does that help with that?
Yeah, it helps, but that depends on how error correcting code memory helps. But then how many bits do you keep for the error correction? Okay, maybe 1 bit, and that may not, the parity bit may not be enough. Literally, we saw the 2 registers and we saw the accumulator. I have a EE background, so this was relatively easy for us. Okay. So this is static master-slave replication. Okay, I'm calling it. That the master remains the same process. It's not as if the slave gets promoted. Okay, and so now that this has all happened, the arrows are going to go to the other direction. and the writing client can go to the writable server master. So the issue still is downtime. Okay, we have downtime problem, and the master didn't change. So now we'll do dynamic master-slave replication, which is what you guys were talking about. So the master goes down, the slave becomes the master. Okay, client goes to the master now, this master now. Okay, and now this other process comes up. It comes up as a slave. Okay, and it gets data from the writable master, and it could even get data from other slaves and the log file, which I haven't shown you. Okay, so I kind of answered this question earlier, but I'm posing it again. Do slaves subsume mirrors? If you had such slaves, would you ever need mirrors? Where a mirror is something that doesn't provide data, doesn't push data to the server.
It could be if you have a really large read-to-write ratio.
You have a really large what?
Read-to-write ratio. So
If you have a very large read-to-write ratio, okay,
so you want mirrors to digest, split the traffic, not get one server, one machine can be handled by the construction. That's
okay. So what you're saying is that if you have lots of reads and very few writes, okay, and that's a very the mirrors are really optimized for such a situation. Okay, that you're hoping that there'll be very few writes to the mirrors and lots of reads. Okay, because then you can have lots of mirrors and you don't bog down the server, writable server too much. Okay, if that's the case, sure, I can have lots of mirrors, but why not have the writable master get data from the mirrors? Why not make each mirror a slave? So you have lots of mirrors, you have lots of redundancy. Yeah.
So presumably the slaves have to check every once in a while if the master is down.
Okay.
I don't know how much computation power that takes, but
Someone has to figure out which,
So-
heartbeat. There can be a heartbeat mechanism, but
you don't need every single mirror to check for that because you've got enough slaves that can, be promoted to masters.
So as long as you need as many mirrors as the number of mirrors you need is a function of how many reads you have and how dispersed the reads are. The number of slaves you need is a function of how much redundancy you need. These are two orthogonal things, right? If there are 10,000 mirrors and I have to take a majority of 10,000 mirrors, my synchronization task is going to be my fault tolerance algorithm is going to be slow. There's a lot of communication here, right? Is that what you're
I
going to
was
say?
just gonna say, like, maybe the way that, like, if you have a single server or something, the responsibility of becoming a master might be a heavier process, whereas mirrors could maybe just, since they're read-only, can run on a lighter weight.
Okay, so the mirrors can run on lighter weight computers?
You have a lot of lighter weight computers to deal with all your reads.
Right.
And you would only have a couple that would need the ability to become the actual master.
Okay, so the computers can be lighter weight and also, the latency. The latency between the mirror and the master has to be low for the synchronization algorithm to work well. And the mirrors are far away. They're far away because latency is an issue, right? And now your fault tolerance algorithm is got high latency. Yeah, Jacob.
I was also gonna say, you might want to keep all the slaves in-house and then from a security standpoint, have mirrors on Akamai, but you want to keep the slaves in-house so that you can configure them as you want and not have to go through whatever you would have to do with Akamai.
Well, excellent. So we keep them in the same data center reduces latency, also increases security. You don't have to trust, you kind of have to trust the Akamai mirrors too, because if they start creating data, and putting up stuff in Macy's, wrong prices, you're in trouble. But that trust is
Right,
lower.
but you wouldn't be like copying or like diverting it as the writable server.
Right. So that's a higher. You need that's a higher qualification, and why put that qualification? Okay, so synchronization time can be high if slaves are on the edge. Okay, which is kind of what I'm saying. Which is and security problems can be high too, and computation requirements can be high if the slaves are on the edge. Okay, so you typically you keep them in a master in a particular data center. The slaves in a particular data center. Okay. So slaves are providing fault tolerance and read load balancing, not reducing the latency, but read load balancing rather than edge performance. Right? So does it make sense to have multiple data centers for the same data? Okay, so we've decided that each data center might have, one master and a bunch of slaves. Does it make sense to have Yeah.
So if you have one data center and like the power goes out or something, then all of the master and all of the slaves would be, out of commission
Right.
for a little bit. So you potentially want the other data center to take over.
Yeah.
that's
So if
not-
power goes down, you want another data center to take over. So that's good. That's one reason. So that says that maybe we can keep them both in Chapel Hill and have one power provider for one data center, another power provider for another data center. Okay, so that could be a reason. Other reasons for having multiple data centers?
Would it be latency across multiple continents?
Latency among the multiple continents. Okay, so if you're Macy's and everybody who makes changes to the Macy's server is in California, then you can keep the data center in California. Okay, and have all the mirrors everywhere that people buy, where the people buy. But if what organization has got writable data across the world? Sorry? Amazon. So the sellers everywhere. Google also, you'll say, has which part of Google? I mean, there's all the search algorithm, search data that probably is kept in
I
California.
think they offer computing services.
Cloud computing services. So your data, okay, and Facebook, right? Lots of people writing from all over the world. So there's a Facebook data center in, probably multiple parts of India, multiple parts of China, multiple parts of. Facebook is in China, right? I keep forgetting. No, okay. So.
More extensive,
So YouTube is not in China, but Facebook is also not in China?
No, nothing hosted on Google servers available in China.
Nothing hosted on?
Nothing belongs to Google. It's
But Facebook doesn't belong to Google.
not Facebook either.
Okay.
They basically buy.
But even the Google search is not available in China?
In Hong Kong, yes, but not in
But Bing is available in China?
yes.
No?
Yeah.
No one uses Bing anywhere. So what does Chinese use for searching?
It's something they use which control the government.
Okay. So let's not take China as an example, maybe, but certainly there's data centers there. Okay, so in India, so multiple data centers of service when you have geographically dispersed writes, okay, and reads, and of course I should add power redundant, power also. Okay, now most of these data centers probably have generators, but still, you want power fault tolerance might be an issue. So now you have multiple writable masters, okay, and multiple slaves. Okay, so a slave is getting data from all the writable masters, right?
This might be going back. The arrows that go to a read-only slave, is that apply?
So I don't want to go back because I'll lose my recording. So what was wrong in that previous recording you're saying?
No, I just don't know what the arrow to a read-only was.
So arrow to a read-only means that the data are going from the source to the destination and not vice versa. Right? So this is, so the slave is read-only, except when we are doing synchronization, when we are doing fault tolerance, then it becomes a source for data also. But in normal operation, it's read-only. Okay? So now you have writing clients going to different masters. A master sends data to all the slaves, whether it's slaves or slaves in other continents. Okay? And it receives data from all the masters. Right?
Just in terms of architecture, I don't think a master, a variable master would directly call a slave it doesn't know to change. It would be sort of
Okay.
It won't be a direct arrow from a
Okay.
master to
So what Nick is saying is that these arrows are logical arrows,
yeah.
telling you in what direction data flow, but the data might flow actually from a writable master in one data center to a writable master in another data center, which can then direct the data to the slaves. And you're saying that is done to reduce the number of messages sent?
I think that's just from the architectural standpoint. Because you want the read-only slaves are basically local copies you keep in a data center, and if you want to make cross data center replication, it has to go through some sort of manager that keeps everything in check.
Okay, so what you're saying is that it has to do it, and the question is why it has to do that. And one reason might be that why have the master know about all the slaves everywhere? The master can go and send it to some process at the other data center, which may not be the master, it's writable master itself. Okay, because why make that a bottleneck? It can go to some other process that goes and says, okay, this is being forked off to the thing. And when you guys study networking, you might have studied multicasting. So multicasting, you send a message to a bunch of places, but the multicaster is smart enough to go and send only one message to the router closest to the destination. So if all the destinations are in one organization, then only one message is sent to the router that's closest to them, and that router then goes and replicates the message. Okay? And you can do application level multicasting also, where you send the message to some application process at the other end, which goes and then creates multiple copies and sends it to the slaves. Okay? So in fact, you often do that. Even the clients often don't talk directly to the master. They may talk to some relaying server that goes and sends it to the master. Because if you're on a low bandwidth mobile computer, you might just want to send a message to some computer with more bandwidth and power, and that can then go and multicast for you, so that you don't have to send multiple data on the network. Okay? So there's all kinds of, there's logical versus physical connections, and this is the logical connections. Okay, Brendan?
If the two clients edit the same bit of data at this exact same time, how would the masters interact with each other?
Okay, so what happens with conflicts?
Two-phase lock.
Okay, so what happens with conflicts is the question, right? And we talked about locking being one way to do it, but locking is a pain because you have to keep the locking state consistent. And in Google Docs, if you had to go and lock every paragraph or every sentence before editing, you won't like it very much, right? So there's lot of non-locking based algorithms also. Okay. There's pessimistic and optimistic concurrency control, and there's serializable and non-serializable concurrency control. So I won't get too much into that, but that is the big issue, a big issue here. Now let's take the example of Facebook. Okay, what could we do to reduce the problem of conflicts? Yeah, maybe we can handle conflict somehow, but it's best if we don't have conflicts. So how would we use this architecture to reduce the problem of conflicts? So Matt.
I mean, you could just say whoever does it first gets to, be the change and then just push it across.
Okay, so handling conflicts involves two things. First, making sure that all the replicas are consistent. A lot of techies said that's what we need to do. The second thing is to make sure that what happened was reasonable. what was expected. So you pushed one, that means you went and, made sure the other person's chain didn't go through, which the other person may not like very much. Okay? Or you go and do it in a certain order, and that order may not make sense. So what I'm saying is that is a cure for conflicts. What's a way we can use to prevent the conflicts, given that we have master-master replication?
One talk to one master and one talk to the other, and then
One talks to, so when you say one client talks to one master, another client talks to another master, and how will that solve the problem exactly? You're right, exactly right, but I want to know.
so you both write, you would see the change reflected, and then later on the two masters would sort out how they were going to merge the change.
Oh, so you're saying the masters still have to sort that out?
Or they could just not. I mean, if you're like Facebook and, you're posting on something and they, two people posted, one posted in, whatever India and one person posted in America, as long as you see the change, the client sees the change that it expected, you didn't really lose a whole lot by not seeing the change.
Okay, so what you're saying is two posts are not conflicting.
Right.
Because maybe the set of posts is a set
Right.
rather than a sequence.
Exactly. And then
Okay?
you can add theirs back.
Fine. So we can go and decide what is a conflict, what's not a conflict. What I'm saying is how to prevent conflicts. Okay? So what you're saying is either how to cure conflicts, or saying that the two operations commute. If they commute, it doesn't matter. So I'm saying these are two non-commuting operations. And how do we make sure that we don't have non-commuting operations?
Are you talking about something that modifies a user's behavior because the conflicts ultimately created by multiple users interacting?
Right. The conflicts are created by multiple users interacting, and we go and you're saying modify the user behavior.
Yeah,
So
you sort of like implying something like that.
I don't know. I don't know what I'm implying. I just want the solution. If there's any solution or not.
You mean like disallowing any kind of non-commutative behavior?
So, but you're saying allow only commuting operations?
Right. And on Facebook, like normally.
No, but if I created a post and you commented, the creation has to happen before you're commenting, right? So I can't quite do that. But if I'm a US Facebook user, can I always go to a particular server? So if I'm a US one, I go to my US server. If I'm an Indian one, I go to my Indian server. You can go to the closest one, but how about having a home center? So that all the home changes, so if I have a change from a mobile computer and from another computer, I have to make sure there's no conflicts between them also, right? So they both go to the same master. Okay? So that master then, sorts out. So we can still have conflicts. I guess I wasn't quite right. I haven't quite prevented the conflicts. But my resolution is a little easier because they were done at one master. So there was a certain order there. Okay? And whereas when you have two masters, there is no serialization point. Okay? So I could always, since the data are partitioned into accounts, and we are hoping that changes to different accounts don't conflict. Okay? I could just make sure that that I always have a home master server and go to that home server so that the conflict sorting out is easier. And if I'm not really using multiple computers at the same time, the reduction is also. Yeah. Nick?
So like if you have requests that changes the same piece of data goes to one server, that will solve the problem. But what I learned when I was doing my presentation was if you do have multiple servers involved, another way to order your transaction is by a global or a synchronized clock, a synchronized timestamp that's uniform globally, so that even in a global scale, when two things are happening at the same time, you know which one's technically happening first.
Okay. So what Nick is saying is that I've tried to reduce the complexity of the problem by having a home server. Okay? But he's saying that you can allow multiple servers, and there are algorithms to address that. They're more complicated than the ones that would be required to address a single master. Okay, am I correct there? Okay. So we are trying to just figure out what the algorithms are. So what I'm saying is, yes, you can go to your closest server, or you can go to a home server. So even when I'm in India, I go to my Facebook server in the US. And now, by the way, did you guys learn in your class the notion of a home server? This is something that is just from my intuition. I don't know whether people do it or not.
I doubt it do because they really care about latency. And if you have a home server and then you move to another continent and latency sucks, the conversion rate is going to drop quite a bit.
Okay.
That means revenue to the company.
So we keep going. So what you're saying is that.
Always do either logging or some sort of synchronization protocol. It's always across multiple servers.
Okay. So the problem that will arise with the closest server is that if I have a laptop that's logged on from India, and I have a remote connection through America to Facebook also, then those two changes could go to different masters, right? If I'm doing a desktop there's that problem, and that problem probably is very peculiar. It probably doesn't occur very often. So you'll just go to the closest server. Okay, I don't know, but it could go either way.
Yeah, but a home server would make sense to handle the conflict.
But like I said, home server is maybe an extreme edge case where, because if you have, only one human being associated with an account, then that human being has to be making changes from multiple places to have a problem. So, but basically, by having multiple accounts, and you reduce the problem. And if you have a master handling a particular set of accounts, okay. So multiple masters can provide load balancing in a single or multiple data center, okay. So even if you have a single data center, you can have multiple masters to reduce the load balancing problem, okay. For geographically dispersed writes, it can provide edge performance. Okay, this is what Nick is also saying, that go to the closest master. Okay. So write conflicts are possible, still possible. And are possible. So disjoint writes. So it can write to home data center. But again with the Facebook example, you can still have conflict rights. So what if I am creating an account with my name with an Indian data center, or I'm creating an account called Smith in America, at the same time somebody else is creating an account called Smith in Germany. Is Smith a British name? It's probably a British name. Okay, so in Britain, so they have to have a common sense of whether Smith exists already or not. And if it doesn't exist, who gets to be the first Smith, right? So we do need, we can't avoid completely the conflict problem with master to master. And then we might need some complex algorithm, okay? And we'll see one of these algorithms in class, okay? So I guess the moral here is that these complex algorithms have their costs. So depending on what the operation is, you might go use one algorithm or the other. Okay? So if I'm writing to my Facebook account, I might just go to the regional server. If I'm creating a new account, I might go to a master or use some very complex algorithm to have master synchronization. Okay? So we've extended our consistency scenarios, and in addition to physical mirroring, we have master-slave replication. And like I said, master, the traditional term is primary and backup. This master-slave thing, did you guys study in your class, this terminology? Yeah. Okay, so when I try to Google for primary, secondary, I got very few hits because now industry's taken over. And master-slave is what is in Wikipedia. There are these MySQL servers. They all use master-slave replication terminology. So I could hardly get, and the thing is, primary backup as such, in ordinary English terms also, that I didn't get many hits there. But that's what, we guys, when I was a student, that's what we studied. Okay? But they're synonymous terms. And we can have master-master replication with disjoint writes, or can have overlapping writes. Okay? And depending on what the case is, we might have different conflict resolution algorithms. Okay? And the conflict possibilities also reduce as a result. Okay.